Welcome to qnawire.
Now we'll work on problem 108 from chapter 13. In this problem, we're given two solutions, and we're asked to calculate molality and the Van Hoff factor. So we're given concentration and mass percent, and we're given the freezing points for a sodium chloride and acetic acid solution. This question might seem a little bit backwards apparent on first glance, but as we work through, we'll see why it's valuable to do problems this way. So we're told we have 1% mass of sodium chloride. So if we have 1% mass, then that means we should have 0.01 kilograms per kilogram of solvent. So that tells us the amount of solute we have. So 0.01 kilograms is equal to 10 grams. And 10 grams we can divide by the molar mass of sodium chloride, which is 58.44 grams per mole, to get 0.171 moles of sodium chloride. So from that, we can calculate molality. We took our solvent to be 1 kilogram, though, so the molality will equal moles. So we know that dt is negative 0.593 because water typically freezes at 0 degrees Celsius. And dt is equal to I mkf. So we can solve for I. The first answer here was molality. Really this one, although it's the same value. And then the second part is to solve for the Van Hoff factor. So I is going to be equal to the dt divided by molality and the freezing point constant. So the molality we calculated as 0.171 m, and Kf we know is 1.86 for water. So if we do this calculation, we'll get the Van Hoff factor. And the value is 1.86. So typically we would assume it's 2 for sodium chloride, but we see that when we actually do an experiment and we measure it, we see that it's not exactly 2. So less than ideal behavior in this case. The second solution that we're given is 0.5% by mass acetic acid. So again, we can just assume 1 kilogram of water, and if that's the case, we have 0.005 kilograms of acetic acid. So 0.005 kilograms is 5 grams, which we can divide by the molar mass to get the number of moles, which is 0.005 0.833. So from this number of moles, we can calculate molality, which is just divided by 1 kilogram, so the value remains the same. So this is our first answer. And then we calculate dt, or we're given in the problem that dt is negative, or 0.159 negative. Again, multiplied by I, M, and Kf. So I will equal to negative 0.159 degrees Celsius divided by our molality, which is 0.0833, and our constant, which is 1.86. When we do this calculation, we get a value of 1.03. Again, acetic acid is an organic acid, so it does dissociate. So we know that it's a weak acid, so it doesn't completely dissociate. And now we see from our Van 't Hoff factor that the dissociation is really very small because it's barely above 1 when we would expect 2 if there was complete dissociation.